The first talk of the day that I introduced a moment ago over in the exhibition tent is called "Is It Me or Is It Getting Hot in Here?" It's not hot in here at the moment, but maybe it will shortly. I need to introduce Mark Faulks to you, and he's one of the 12 fellows of the Institute of the ISCVE. So that should tell you a lot about his standing within our industry and the fact that he's been around for a very long time, chipping away at things. And Mark also serves on the council and has a particular interest in STEM education for young people as well, and has been very helpful in putting together resources for our ambassadors to use. So without further ado, I'd like to ask Mark to come up and give us his talk. Thanks, Mark.
Thank you. Oh, what a lovely introduction. What a lovely sea of faces. I think several of whom I know, which is good. So yes, I've been in the AV industry for 20 years. I know I don't look old enough to have been around in the industry that long. No, somebody responded. Things have changed a lot in that 20 years. We've kind of gone through this transition from analog to digital, and now we're moving into kind of the IP phase where everything's now starting to go over networks. And over that time, we've made things more efficient, and things have got smaller and cooler, but all of a sudden they're getting hotter again, to the point where I think it's actually starting to become a problem. So my intention today is to talk about why that's a problem and what we can maybe do about that, but I put the word maybe in there because I've rather foolishly chosen to speak on a subject that's not my area of specialism. Not because Doug suggested that's because I'm trying to stretch myself. It's actually because I think this is a conversation that we need to have, and it's a conversation that needs to carry on, but we don't seem to be having it. So I thought I'd try and start it, in the hope that there's some far cleverer people than me in here who can actually take this a little bit further. Is it getting hot in here? Yes, it is. But if I sat down now, that really wouldn't have used up much time at all. So let's move on and look at the three questions that I'm going to address. Why is it getting hot? Why is that a problem? And what can be done about it? So starting at the beginning, why is it getting hot? Let me see if I can keep everything in sync. I've got my notes on one and the presentation on another, so I'm trying to click in two places to keep going. So why is it getting hot in our AV systems? Because electrical devices produce heat. They always have done, and they always will. But why is this suddenly becoming a problem? And I think the reason for that is because we're suddenly producing a lot more heat than we were, and it's been a very sudden change. Now, yesterday, Andy Doherty, that's the guy's name. I had it in my head for ages, and then, of course, the moment you go to say it, you lose it. Andy Doherty was talking about the impact that COVID has had, and actually, I think part of this issue with heat has actually been influenced by COVID. And the reason for that is because pre-COVID, actually I need to just set the scene slightly, just rewind slightly. I'm mostly going to be talking about video conferencing and meeting room systems because that's what I work with a lot. So sorry to those of you who don't work with those kind of systems, but I think actually the stuff about heat is quite relevant anyway. But a lot of my examples are going to come out of the video conferencing side of things. Pre-COVID, when we had meetings, people tended to turn up to a meeting. Everybody came into the meeting room. And if you had somebody join remotely, it was generally done by a little spider phone that sat in the middle of the desk. And they were rubbish because they were based on telephony. And the quality of audio over telephony is rubbish. But everybody expected that. Everybody knew that if you were using a speakerphone, that when the person at the far end spoke, everybody had to be really quiet so you could hear them because the audio quality wasn't very good. And when you were speaking to the person at the far end, you had to look at the speakerphone and speak very loudly so that you could be heard at the far end. And then COVID came along, and suddenly we couldn't all be in these meetings, and so we all went to Zoom and Teams, and everybody joined the meeting from their own laptop. and they had their own little microphone right in front of them, and their own little camera, and their own little speaker, and it all sounded lovely. And then we went back to big boardrooms, and we said, hey, we don't all want to travel to these meetings. Let's have some people in the boardroom and some people at home on a Teams meeting. And the people at home on a Teams meeting had their own little microphone and their own little speaker and their own little camera. And suddenly there's all these complaints. Well, when we ran these Teams meetings during COVID, I could hear everybody brilliantly, and I could hear everything, and everybody could hear me, and I could see them. Why can't I have that in the boardroom setting? Well, you can, if you give everybody their own microphone, their own little speaker, and their own little camera. But we don't do that. So we put a couple of big cameras in, a big microphone, and some big speakers. But it doesn't work because the cameras are too far away, the microphones are too far away, the speakers are too far away, and we've got all this reverb and noise in the room. So somehow we've got to try and get rid of it. But it's fine, because we've got AI. We can bring AI, we can bring in AI noise reduction, we can put in beam steering speakers, we can put in beam-forming microphones, we can do acoustic echo cancellation, we can do all this lovely digital processing. And it's great, and we'll pack it into this tiny little box, and we'll stick it in a tiny little cupboard with no vents in it. And then we'll go, hang on a minute, why is it getting hot in here? And the reason it's getting hot in here is because we've taken all of this clever electronics, which produces massive amounts of heat, and put it in a tiny little cupboard, because nobody wants to see anything anymore. A few years ago, we worked on a project. Look at my friend Liam over there, who I used to work with. We worked on a project in central London. We were putting some meeting room systems in, and they've got this brand new building that they were building. In fact, they demolished their swimming pool, and they rather foolishly demolished their swimming pool, filled it all in, built a new building on top of it. It's like, well, you could have just used the old swimming pool as a plant room underneath. But they didn't. They just leveled it off, built a new building. There was this, we looked at the drawings. Here's an AV cupboard on the side of the boardroom. And it just, it took a little corner off the kitchen, and the CEO looked at the plan and said, oh, I don't like that lump taken out of the kitchen. I want a nice square kitchen. Get rid of that cupboard. Well, where are we going to put all the AV gear? Oh, can you just put a wooden cupboard in the corner? Just a little one with, we'll just cram all the gear in there. That'll be all right, won't it? Well, we kind of made it work, but it wasn't great. And so these are the challenges that we're facing. Everybody expects not to see everything. Everybody expects everything to be tiny and to fit in these little cupboards with no ventilation. And so things are getting very, very hot. And it's becoming a problem, which I think as an industry we need to address. And part of that is actually we just need to stand up to clients and say, no. It's not an easy word for AV people to say. Actually, just repeat it with me. No. I think this is an important thing that we need to learn. So let's actually move on to some of the more technical stuff. So the first law of thermodynamics, there's 4. We start at the 0 floor, but there you go. Well, I'm only going to look at a couple of them. So first law, when energy passes into our outer system, the system's internal energy, it changes in accordance with the law of conservation of energy. Basically, if we have a thing and we put energy in and some energy comes out, if less energy comes out than went in, then there must be more energy inside the system. So if we then look at that in terms of an electrical device, we have electrical power going in, we have work being done by the device, and the difference between those two is the energy that's now stored in the device. So I've got far too many animations in here. So we actually have some energy which we're storing, but we may also have an awful lot of heat which we generated, which, if we know about the second law of thermodynamics, if we've got a hotter body next to a cooler body, then that energy will transfer. Because it will basically create a change in temperature, and then with the temperature change, that will force the energy to flow. So why is this heat a problem? Well, actually, heat is not a problem. Temperature is a problem. Essentially, when our equipment starts to get hot, it starts to misbehave. And one of the main things that we will start to see is intermittent faults. Now, there's lots of reasons for intermittent faults. Sometimes it's a problem in the firmware. It's programmers putting bugs in systems or memory leaks. Sometimes it can be the network, and sometimes it can be thermal issues. And there are ways we can tell the difference between these. Generally, if it's a bug, it's reproducible, so every time you do a particular thing, it will go wrong. If it's a memory leak, it means that basically, as we're running the process, it's using more and more and more and more memory, and eventually it runs out, and then the system falls over. But that will take quite a lot of time. Both of those things, if you reboot the device, the fault will clear, and until you do the same thing, or until you leave it running for roughly the same amount of time, you won't see those problems again. You might also see something in the logs that suggested what went wrong. Now, if it's a network fault, it's probably only going to affect your data, because it's only data that's moving over the network. Your main program will keep running. So one of the projects that I've been working on recently, we've had an AV contractor who keeps blaming the fact that the USB device keeps failing on the network. Oh, it must be a network issue, because the network was installed by another party, so that's not their problem. Oh, it must be the network, it must be the network. Well, how is faulty network packets causing the USB device to fail? That's not a USB issue, because the USB device is nowhere near. We've got two lots of memory. We've got the program memory and we've got the data stream that's coming through. If the USB device is failing, that's something in the program. So what might have caused that? Well, it could be a thermal issue. Essentially, as these things get hot, our silicon chips get hot, and essentially we start to get glitches in there. So what should have been a 1 becomes a 0, what should have been a 1, what should have been a 0 becomes a 1. And essentially, if that starts happening in our program space, then we might suddenly say, well, we're currently here in the program, or we need to jump to this point in the program, but we get a bit error in there, and suddenly we jump to this point in the program, and now the whole stack is completely wrong. And so our process just goes and falls apart.
That's a technical term.
That is a technical term. The technical term for faulty programs is
How do you spell that?
badly, generally. So that's potentially a big problem, and we potentially need to do something about it. So what can we do about it? We can implement some good thermal management. So what does good thermal management look like? I'm going to talk about 3 different steps in good thermal management. So we need to, that's where this has gone horribly wrong. And in fact, the problem is that I've made some slight tweaks to my presentation on my laptop and then forgot to put that on my memory stick. So what you're looking at is not the version that I'm looking at. So this is going to get fun. So what I've got on my screen is identify a suitable operating temperature, identify how much heat will be generated, and then determine how to remove excess heat, which means this is probably going to go to the wrong slide. Yes, it is. Excellent. I've now got my slides in completely the wrong order. Good. It's always great when you do lots of work on something. So how much heat will a device generate? I'll follow what's on your screen rather than on mine. So that will depend on the power consumption of the device and the thermal efficiency of the device. Let's see where we get to next. Amplifiers. So Jamie's done some fantastic presentations over the years on amplifiers and their efficiency, and I know far less about it than Jamie does. So if you've got any questions about amplifier efficiency, please ask Jamie, not me. But this is a rough guide as to how efficient amplifiers are in terms of power consumption and thermal output, not to do with workload. The actual power consumption will depend on the workload. So depending on the audio signal that you're putting in depends on how much power it will consume. But this is an indication of the thermal efficiency. So with how much power it's consuming, how much thermal output is it going to have. I'm keeping an eye on Jamie because I know I'm going to get in trouble if I say anything wrong here. I'm sure she'll tell me afterwards. That's fine. But essentially, Class A amplifiers actually were very thermally inefficient, which is why we now tend to use Class D and above amplifiers. We get a lot less heat out than we do with the older Class A amplifiers. Just as an example, if you were trying to get 100 watts out to a speaker and you've got a Class A amplifier that's 50% efficient, that means you're actually going to use about 200 watts and you get 100 watts of heat. Whereas if you do that on a Class D amplifier, you're going to use 125 watts and get 25 watts of heat. 25 watts is slightly less than a T-light. T-light kind of produces about 30 to 40 watts, depending on the actual composition of a T-light. Interestingly, if you, when we get on to some of the DSP stuff, in fact, which we'll get on to in just a minute, I'll come back to that in a minute. So DSP, audio DSP, computers, video scalers, encoders, decoders, things like that, generally less than 10% thermally efficient. So if you've got a 40 watt DSP, it's probably producing between 36 and 40 watts of heat. In fact, some of the DSPs are about 1% thermally efficient. Because essentially they're not actually doing any physical work. All of the work is just in the processing, which means all of it becomes heat. Typical power consumptions, audio DSP for a small meeting room, about 40 watts, so it's about a T-light's worth. And when you think about that, if we're putting our audio DSP into a small wooden cupboard with no vents, that's basically the same as going home, opening your kitchen cupboard, lighting a T-light, putting it inside and shutting the door, and expecting it to be okay. Now, I think most people would know that's probably a stupid idea. And yet, when we start installing AV systems, we think it's a good idea to put an audio DSP in a cupboard with no ventilation. And then when you start to go to slightly larger systems, so by the time you're up to a large meeting, you've maybe got 100 watts of DSP power in there, and then you add in your little PC that's actually running your Zoom room or your Teams room, and you've got another 100 watts. You stick in a video scaler, maybe a multi-window processor, and then if you want really fancy stuff, and you've got AI camera tracking, you've got another 350 watts. And most of these devices are getting on for about 1% thermally efficient. So if you add that up, you've got an awful lot of watts of power. You've got sort of, 10 T-lights worth of power, 10 T-lights worth of heat being generated inside your AV cupboard, which is not ideal. I seem to put lots of mathematical formulas in here just because it amused me to do so. Please don't pull me up too much on the maths. So operating temperature. Generally, our target for operating temperature should be about 11 degrees C below the maximum operating temperature of the devices that we're working with. 11 degrees C might seem like an odd temperature. It's because it's Americans. It's 20 degrees Fahrenheit. But research has kind of suggested that actually if we go with that 11 degrees C below maximum operating temperature, that gives us a good, stable lifetime. And actually for every 5 degrees we go above that, the life expectancy of our device actually drops by about 40%, but our reliability drops by about 50%. So, actually just a 5-degree temperature shift inside your rack and your system becomes a lot less reliable. You're much more likely to see those processes starting to get glitches and fail. So how are we actually going to remove the heat? So as our system runs, it's going to generate heat and the internal temperature of our system is going to rise, and then that's going to cause heat to flow from our system into its surrounding environment, and that is a continuous process. So if we've got 40 watts of heat being generated, we need to be removing 40 watts of heat. So that's 40 joules of energy every second, and so every second we need to get 40 joules of energy out of that system to maintain a consistent temperature. The main ways that we're going to transfer heat are via conduction, convection, or radiation. Conduction is really useful for moving heat around. So if we've got something that's metal, something like a heat sink, we can move heat from one place to another. Problem is we're still actually physically coupled to the system, so we've not removed the heat, we've just moved the heat. Convection will actually let us remove the heat, so essentially we can heat up a fluid that's by a device and then move that heat away, so we can actually remove heat from the system. And some heat will be removed by radiation. Radiation heating doesn't actually have that much effect. It's to do with the surface area and how efficient something is at emitting heat, and it's based on the power of 4 temperature difference between stuff, which means it does shift as the temperature, the amount that it does shifts with the temperature variation. But if you're looking at around sort of 20 degrees C, and if that's your ambient temperature and your system temperature is around 29, you're losing per square meter for a jet black device, which is emitting 100% radiation, you're losing about 3 watts per square meter of surface area. If you consider a 1U rack device has a surface area of about half a meter and is probably about 50% heat emitter, then you're losing about 3/4 of a watt per degree from a unit. So you only lose, if you've got a 6-7 degree change, you're losing sort of 5 watts of power. It's not really actually going to achieve that much. So our main source of heat loss for a system is going to be convection, and we can either have natural or forced convection. So if we're natural convection, then essentially as our surrounding fluid heats, its density decreases, and then thanks to gravity, essentially that's going to rise, and then colder fluid is going to drop in its place, and that will keep going. And the actual rate at which that happens depends on the temperature difference between the thing that we're heating and their surrounding environment. But it does also rely on gravity. So if you're ever installing AV systems on the International Space Station or anything like that, just bear in mind that natural convection isn't going to work very well. So I don't know how many of you are doing space station installations at the moment. Anyone? No? Space station installations. Are you installing AV equipment on space stations?
I don't think convection is going to work on the space station.
No, that was my point. It wouldn't work. So if we use forced airflow, then essentially we're using a fan or a pump to actually move our fluid through the system, and our fluid velocity is then determined by our actual fan. Now if we've got a closed system, then we're just churning that fluid around inside our system, and again we're not removing that. So potentially what we actually want is an open system, so we're going to bring cold fluid in, heat it up, and then take it out. And at that point our cooling rate is actually more dependent on the heat capacity of the fluid and the volume of fluid that we're pumping through, provided we've actually got enough velocity in there to actually absorb the heat from the surface they're running past. But in general, by the time you've got enough volume flow rate, you've also got enough velocity in there. So actually, all the stuff that I've said about formulas, for all those previous formulas about convection and conduction and radiation, actually fairly irrelevant. The one that we're particularly concerned with is actually the thermal capacity or the heat capacity of the fluid that we're running through. In general, we're using air, and although it does depend a little bit on the temperature, at the kind of temperature range that we're looking at, it approximates to, we actually need a flow rate of about 1.76 cubic feet per meter per watt per Kelvin. So if we know how many watts of power we need to remove and what temperature difference we need, then we can work out roughly how much airflow we need. If our system needs less than about 285 cubic feet per minute, we can maybe get away with natural convection, assuming we've got some gravity to actually work with us on that. Once we get above that, we're going to need to be using forced air convection to actually cool systems off. So let's have a look at some applications. So if we're trying to cool an individual device, we need to make sure we have got adequate space around the device for airflow. Now, in terms of adequate space, generally, if you've got a fan, you need clear space that is equal to the diameter of the fan in order to get enough air in. If you've got less space than that, the fan is going to struggle to pull enough air through the space. Also need to make sure that we've got our device correctly oriented to allow for the internal airflow, particularly especially if it's passively cooled, so if it's not got a fan inside it. And we also need to make sure we've got a suitable air intake temperature to get the right level of cooling. This is a very bad diagram of a passively cooled device. So you can see we've got some airflow going through this device, and it comes in at the left, goes across our silicon chip, and then goes through a power supply. Our silicon chip will pump some heat into that air as it goes through, and it will then run through that power supply, pick up some more heat. If we tip that on its side, if we put the power supply at the top, then air will come in the bottom, go at the top, and all will be well. If we put it up the other way, however, our air is going to get heated by the power supply before it gets to the silicon chip, and so our air is going to be much hotter, and our chip is going to start overheating, simply because we put it up the wrong way. This is a very, very bad idea. Unfortunately, with most devices, what that would actually mean is if you put it up the correct way, assuming that that's an okay thing to do, it would mean that all the connectors are actually on the top. Whereas logically, we like to have all the connectors on the bottom so that any dust doesn't fall into the connectors. And we have all the cables nicely coming out the bottom rather than flapping around out the top of the device. But from a thermal point of view, that's probably a bad idea. But then if we start piling all this stuff into a cabinet, we need to think about how we're going to manage a whole cabinet's worth of kit. So we need to meet the thermal requirements of all the individual components, which means our target operating temperature actually needs to be 11 degrees C below the maximum operating temperature of the lowest rated device. So if you've got 6 devices in your rack that have a maximum operating temperature of 50 degrees C, and one that has a 35 degrees C maximum operating temperature, then your target temperature needs to be 24 degrees C. Because if you keep all the others cool, because they'll be fine at 39 degrees C, but you're already 4 degrees over for your most sensitive one. So we need to make sure that we're actually looking at what's the lowest rated one. And then we need to make sure we've got adequate airflow to remove excess heat from everything that's in there. So we just need to add up all of our heat output and make sure we've got enough flow for that. So, some common problems. Avoid overloading enclosures. So here's a nice little enclosure. It's got some devices in it. It's got a little fan at the top that sucks the air out. All is well. Hang on a minute, need to put another device in there. So let's make some space, and I'll put another device here, because there's some rear racking. I can fit a device in there. But now I've got rather awkward air, so I've got this lovely little air pocket down the bottom where I've got an awful lot of heat, and that new device that I put in the back there is going to get very hot, and in fact the one at the bottom is going to get quite hot as well. So, bad idea. Let's not do that. Avoid putting intake fans too close to your exhaust fan. If I've got a little passive device in here, I think, oh, let's put some ventilation in there as well, get a bit more airflow through this rack, rather than just the stuff that's being forced through devices. So I'll put one in by my passive device, and I'll put one in at the top as well. That'll help get some more air through my rack. Well, it will, and it will all come through the top there. And my little device down the bottom there will still get very hot. So actually I need to close that off, and then I can start forcing air through there as well. Avoid drawing, so recirculation, avoid drawing in warm air that's already passed through a device, unless it's designed to operate in that way. So this is a series of devices that actually are designed to draw air through multiple devices. So this isn't actually recirculation, and it is designed to do that. It essentially means that each of those fans has to be able to draw about 3 times more heat than it would if it was just a single device. Reverse flow. So the enclosure flow rate must be greater than or equal to the sum of flow rates of all the fan cooled components. Otherwise we start to get this interesting situation where actually if our fan at the top isn't pulling out air as quickly as is being shoved into it, then where we've got passive components, actually we'll find we're pushing hot air back over the top of them. Actually we're making them hotter rather than cooler. Again, not a very good idea. Poor convection. Yeah, be aware of where the vents are on devices if you've got stuff that's convection cooled. This is especially if you've got, I'm sure nobody here uses nasty, cheap domestic devices that are made out of plastic. If it's metal, then the outer casing is probably acting as a conductor. If it's plastic, it's acting as an insulator, which means you are totally reliant on the air flowing through the device. If you've got side vents or front and back vents, that's kind of okay because you can blow a fan at it and it will force the air in. If you've got vents on the top and bottom, if you blow air across it, what you're actually doing is decreasing the pressure inside the device. And actually, you'll get less convection and therefore it will get hot faster. Plus, it's now sitting in the middle of a cabinet, so it's already got more heat around it than it would have had if it was just on a nice little shelf. So, additional challenges that we might see. I did have a few more slides that I've got on here, which I forgot to copy across. So, impact of heat from the enclosure on the ambient temperature. So, if we've got a cabinet that's producing a lot of heat and it's pumping into the outside environment, actually, what's happening to that heat? Because we're now just heating up another space. If we've got a nice AV cabinet and we put it in a cupboard and it's a very small cupboard, does the cupboard lose its heat fast enough? If not, actually, as well as managing the heat inside our cabinet, we also need to try and manage the heat inside the cupboard. Now, we might be able to say that's somebody else's problem, but we need to make sure that they're aware of that and that's being dealt with. Otherwise, our temperature is going to go up of the air that's coming in, and our lovely flow rate that we calculated now doesn't work because we've got a much smaller temperature differential between the two. If you have got particularly high thermal outputs, you might want to change the fluid that you're using. So maybe use something that's water cooled, because actually the heat capacity of water is about 4 times that of air. So actually if we pump water through, we only need about a quarter of the flow rate. Or the other thing you can do in order to increase the rate at which you actually cool stuff is to just cool the fluid before it goes in. That's quite popular in data centres. They actually use refrigerated air that they pump through the systems, because it just means they can actually reduce the volume of air they have to flow through because it's colder. And I think I've quite nicely used up most of the time, so I can't take too many questions.
Certainly given us a lot to think about there. If we have any questions, it's important that your question is spoken on a microphone because we are live streaming. Have we got a roving mic, please? Perfect. Have we got first question in the second row over there, please?
2.
Thank you.
Yeah, I'm normally the one handing the mic out. I'm just curious about your plan of the maximum operating temperature for devices, because to me, because I work in AV and setting up PA systems, so that 11 degrees threshold, that seems quite high to me. I'll give an example. So at the weekend, I was setting up a DJ stand, and we had a PA system with D&B D12 amplifiers. They're modern digital amps. They're a little bit older, but they're still fairly efficient. And I was monitoring the temperature, and they got up to 49 degrees during the gig, but their maximum operating temperature is 75 degrees, which, but I was feeling the front because it blows air from the back towards the front, and it still feels quite hot. So is there any other practical considerations other than the position of static airflow that you need to also think about in a temporary system setup?
If it's a temporary setup, you've got a little bit more flexibility because you're not expecting the system to maintain that for a very long period of time. A lot of installed systems, for various reasons, they don't very often get turned off. So you've got you've got a long-term, very consistent high temperature in there. Things like systems like that, where you've got a lot of air flowing through there, if you've not got anything surrounding it, if it's got sort of free space in which to pull air through, you've not really got an issue, because you're not creating a higher temperature inside there. Your air intake is still coming in at whatever your ambient temperature is, so 20, 25 degrees. And even if you're, if it's coming out sort of 45 degrees, it's running 45 degrees internally, the temperature of the air that's actually coming out the front won't be at 45 degrees. It'll be much less than that. What you're trying to do is you're trying to keep that temperature down. I mean, in terms of if your maximum operating temperature is 70 degrees on those amplifiers, then the maximum you're going to want to hit from a long-term sustainability point of view is 59 degrees. So if you're still coming out 45, that's not an issue. The challenge is if you try and put those amplifiers into the same rack that's got its own internal airflow, as well as some signal processors that actually won't cope if they go above 40 degrees. Because if your amplifier is kicking out a lot of hot air, because it's generating a lot of heat, then you don't want that anywhere near your DSP. Now, if you're setting up a temporary system, you can have two racks, and they've got a couple of meters or meter or so space between them. Then it's not really a problem.
So would you be more concerned if you had a set of audio amplifiers in with a set of video processing, for example, which might have a lower operating temperature?
Yes, that's where the real concern comes. It's making sure that you've got enough cooling and enough space to make sure that the heat from those amplifiers isn't then getting pumped into your audio processors. Because if you've already heated the air up and you're then recirculating it through your audio processors, essentially you're bringing your temperature differential inside that audio processor down to a very, very small rate, which is going to have a massive volume of air flowing through. And the internal fans in that DSP probably aren't designed to cope with that. They expect the air temperature that they're bringing in to be less than 25 degrees. If you're chucking in 30-degree air and expecting it to keep the temperature down at 35 degrees, that's a big ask. That's a lot of volume of air you've got to bring through there.
An observation, if I may. That question was great because it did show what we were talking about yesterday, which is the breadth of our industry and the difference between the disciplines within the industry, because that's a question of from a live sound perspective versus an installed sound perspective, and it shows that the disciplines are subtly different and there are different considerations that need to come in. So thank you for that question. That was very timely, I think. One last question. Was it Jamie, did you have your hand up?
I was only going to make a comment.
Could you use a mic? Sorry. Thanks.
Oh, I was just going to make a comment, really to do with, I would put less than 1% for most non-power amplifier or non-power applications, to be honest. Basically, everything you put in comes out as heat.
Yeah.
If you do that, you won't go wrong. But I was going to make a comment on reliability. Changing temperature makes a huge difference. So, I mean, I know you had an aim of 11 degrees below maximum, but if you were able to drop that 5 degrees, or 10 degrees, if it's possible, it goes up and up. And finally, environment. And again, we think about something like a nightclub. When you start up, it's nice and cool, the air going over the equipment's nice and cool. As soon as you've got, every 4 people dancing is about a kilowatt. So it gets hot quite quickly. And suddenly you've got an ambient temperature that's much, much hotter. So sometimes it's quite hard to work out what the worst case design scenario is. I mean, and especially, when you're dealing with variety of numbers of people in the space or environmental facts. I mean, I had a piece of kit I designed that I worked hard on the thermal design, and it didn't work in New York in the summer because it just got too hot.
Yeah.
What can you do?
Yeah.
Well, look, thank you very much for those insights, Jamie. It's always good to hear them. Could we please give Mark a very big round of applause for a really useful presentation? So it's time to head back to the tent for a tea break, and please do take a moment to have a look at the stands and see the exhibitors that have come to see you. And the next seminar will be at 11:30. Hope to see you all back here then. Thank you very much.